In RF engineering, signal values can range from extremely small power levels to extremely large ones. If we try to represent everything on a linear scale, the numbers quickly become impractical to compare. In this lesson, we will learn logarithms and why they are the foundation of how RF engineers measure and compare signals. In everyday mathematics, we are used to working with linear numbers where differences are absolute and easy to interpret. For example, the difference between 1 and 2 is the same as the difference between 100 and 101. This works well for many physical quantities that vary within a limited range. However, RF engineering deals with signals that can span extremely large dynamic ranges. A weak signal received by an antenna may be measured in nanowatts or picowatts, while transmitted power can reach watts or kilowatts. Representing both on a linear scale makes comparison difficult and often misleading. Because of this, linear representation becomes impractical in RF systems. Engineers need a way to compress large ranges of values into a manageable scale that still preserves meaningful relationships between signal levels. A logarithm is a mathematical operation that transforms multiplication into addition and compresses large numerical ranges into smaller, more manageable values. Instead of working directly with raw numbers, logarithms describe how many times one value must be multiplied to reach another. In RF engineering, this transformation is extremely useful because signal chains often involve multiple stages of amplification and attenuation. Each stage multiplies or divides signal power, and logarithms allow these multiplicative effects to be converted into simple additive relationships. This makes system analysis much easier, especially when dealing with cascaded amplifiers, transmission losses, and overall link budgets. Another important reason logarithms are used in engineering is that human perception itself is often logarithmic rather than linear. This means that we perceive changes in sound, light, and signal strength in relative terms rather than absolute terms. For example, doubling a signal power does not always feel like a doubling in intensity. Instead, what we perceive is closer to a proportional change. Logarithmic scales align mathematical representation with how systems behave in practice. This makes log-based measurements not only mathematically convenient, but also physically meaningful when interpreting real-world signal behavior. In RF engineering, logarithms allow engineers to convert complex multiplication chains into simple addition problems. For example, when multiple amplifiers are connected in series, the total gain becomes the sum of individual gains when expressed in decibels. Similarly, losses in cables, connectors, and free space propagation can be added directly in dB form instead of multiplying attenuation factors. This dramatically simplifies system-level calculations. Because of this property, logarithmic representation is used almost universally in RF system design, measurement, and analysis. In RF engineering, logarithms are not just a mathematical convenience, but a core part of how signals are measured and interpreted. Units such as decibels dB and decibel milliwatts dBm are built directly on logarithmic principles. These units allow engineers to handle extremely wide signal ranges in a compact and intuitive way. Whether analyzing antenna gain, path loss, noise levels, or amplifier performance, logarithmic scaling provides a consistent framework for comparison. Without logarithms, RF system design would be far more complex, requiring constant manipulation of very large and very small numbers across multiple stages of signal processing. In this lesson, we learned that logarithms compress large numerical ranges into manageable scales and convert multiplicative relationships into additive ones. They are essential in RF engineering because they simplify signal measurement, system analysis, and performance comparison across wide dynamic ranges. In the next lesson, we will explore decibels dB and dBm and see how logarithms are directly applied in practical RF measurements. If you found this useful, like the video, subscribe, and follow for the next lesson.